So I'll start with a quick introduction. So Silas, I think everybody knows him in the room, so, but this is his third talk at a Bitcoin conference. This is part 3 of his Digital Logic series.
You don't need to see part 1 and 2.
Yeah, you don't need to see part 1 and 2. He's going to start from the basics and build up from there. He got interested in computer science maybe a couple years ago. We just ran through this an hour ago, so he's been working on that. But yeah, so do you have any other? Oh yeah, so there's puzzles in the back where Peter's sitting. We developed these together, so I think everybody has already either bought one or knows about them. So shout out to you. So should we start with, can we get started? Yeah. You start with binary?
You might hear me? Oh, that's there. Would you like to hold the mic?
You want to hold this? I don't.
So, here's the logic sim. There's pins on this side and pins on this side.
Yeah, it's fine.
So, you can turn the pins on and off. You can put stuff in between and connect it up to the machine. And then, once you're done, you can save that and turn it into your own logic, which is why almost all of these have something inside. Well, except for this one, which has a bit of code inside. So, I'm going to start out with, okay, goal is to figure out memory. So, I have a few ideas. One idea is, okay, I should probably introduce the gates first. OR gate, strong gate. The gates have like 2 inputs and 1 output. So if either this one or this one is on, then the output is on. Very useful. Transistor. The name is a little bit misleading, but how it works is there's a good apple and bad apple, and the output can only be let through the condition that this is off. So that's the only way for the output to be on.
You called it a good apple and bad apple inputs?
Yes. Okay. AND gate. Also pretty strong gate, except it's mostly off and shipless. So if both of these are on, then the output is on. Like that. XOR gate. Now this one works well, there's many interpretations. It could be this is on and this is off. It's on, this is on, and this is off. It's on. If they're different, it's on. If either of them are on, but not both of them, it's on. There's many interpretations, but this is what it looks like. Okay, I have to start actually getting into the thing. So, this is on. I'll put that through an AND gate with the output.
So you said your goal is to store data, right?
So exister is off and the output is off. I think I would rather go the other way. That doesn't have any setup. For this case, if I put an OR gate, so either the input is on or before the output is on, then this should be a little bit more interesting. So now if I turn it on, then the output is on and it moves back to the input. But if the input turns off, then the output is still on, so there's no way to turn it back off. So I figured out how to set a 1 to it. I think I can figure out setting a 0 to it. But first, I'll connect this to the other input, like that. So I'm going to have another signal that will turn it off. And what this will do is it will, instead of taking this straight to here, I'm going to have to bring it to a transistor so that this has to be on and this has to be off. And then I'll connect it back to the input. Okay, does this work? If this is on, that turns it on. If this is on, that turns it off. Okay, that looks about right. I'll call this the SR-Latch, or set reset latch. Now, I think I can store data. So,
do you want to show the implementation of the SR-Latch real quick?
When I did this at first, it looked more like this, but it still works. So, now I want to have a data signal and a signal for storing that. So if this is on, if this is on, then the SR-Latch should turn on. But if this is off and this is on, which you can test for like this, then the output should turn on. Okay, does this work?
Sorry.
Okay, nothing's happening. I'll store it.
Sorry.
Yep, looks about right. If it's a 1, I'll store that, and it's still on.
Can you do that again? Stream off for a second.
So storing a 0 turns it back off because it's resetting the thing, but storing a 1 turns it back on. I'll call this the data store. So there's a slight problem. The problem is that, okay, if the data you're trying to store changes when you store it, then that can lead to some pretty weird stuff. I just wanted to store this data that should be on, but nope. So to do this, I need to only store the data right when it turns on. Because then the data, by the time the data changes, the store signal will already be off. I'll say 1 tick is the shortest unit of measurement in the system. So here's a diagram.
In time?
Yeah. Here's a diagram of what the input could be and what the output is.
Yeah, right big so they can see.
Okay, and I want this to only be on at the tick. At the tick where it just turned on. So no, 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 yes, no, 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 no.
So is this time going from left to right?
Yes. So I noticed that this part, what's unique about it is that this one is off and this one is on. So I'm going to add one more line. If I show the delayed version, delayed by 1 tick, then that would go something like that. So now, if the input is on, but the delayed input is off, then the output is on. So that's how to
Was that supposed to be 1?
No. I was just connecting it up. So, do you have a whiteboard eraser?
No.
My hand works too.
So I don't quite understand this diagram, but I think once we show it in your implementation, it might make more sense. Does everyone follow the diagram? Peter's got it, so good to go. Yeah, okay.
So, what that means is, if the input just turned on, then that means the input is on, but the delayed input, delayed by 1 tick, is off. So, how do I make a delayed chip? First, I'm going to finally use the XOR gate. And in this interpretation, turning this on changes the input. So, I'm going to do something like this.
So what's happening?
If the input is on, then it switches itself. So now it's just switching rapidly.
Every tick it's turning on and off. I don't know if they can see that in the projector, but that's why it's a little darker. It's like a half tone.
Yeah. So I'll take this. It's called, yes, of course I made tic-tac-toe here. It's called this. And yes, that does stay.
So it says TCONTC What does that mean?
It means to change or not to change. That was the question. So now, what if I have the data change when it is not? Okay, what if I ask it to change when it is not the data? So what if I have this go to the output, but also XOR gate, this goes over here, like that. So now, if this turns on, and this interpretation of the XOR gate, if it's different, it's on, but they're all the same gate. So this will be different. It says, hey, the output is different. Asks it to change, and then this loops back around, and now both of them are on. This should work. As you can see, when the data changes, it flashes, telling it to delay. So I implemented this as misspelled delay, D-L-A-Y. And now, sorry.
Can you show me what the implementation for your delay is?
It was literally exact.
Oh, okay. Sometimes he uses a more compressed version. Production.
Yeah. So now, if you remember, the rising edge circuit should only turn on if the delay is off, but the input is on. So I can test that with the transistor right here. If this is off, but this is on, then the output is on. So does this work? Huh? I think it
So it was blinking, the output was blinking when you turned it on.
Also, if someone entered the room while it's doing the talk, then shout out to you. Yes. So, this is, my name. This is called the rising edge. Right circuit. And it works like.
But that's the same, so it's a different implementation, but it produces the same result.
So now I can make the final thing. If I have the store signal go into a rising edge and then a DS-Latch, and then output that, then that should work. Okay, storing, now it already flashed, so it's not storing. If it's on, then it will store, and then it won't turn back. So I call this, okay, final thing, the data latch, or D-Latch, but it's pronounced data latch. So final test. If I have this going to the store signal, and that going into the output, also this is, if you were here from the beginning, you might have seen this on the projector because I forgot to take it down. So here it is. Final circuit of this stuff. Yep, it's stored properly.
Yay!
Okay, that's Hey, you didn't even let me say that that's the end of the talk.
It's an impressive result.
Wait, you're not done? You're gonna, there's some, so that's the end of that, showing the implementation, and he's taking this a lot further. What other things have you implemented based on this?
Well, there was something I learned before this, but I didn't have to implement it, even though you usually do that first, which is learning how to add numbers in binary, because binary is a big part of, like, this can only be on or off. So,
You also mentioned registers.
yeah, if you wanted to have 1 byte of data, which is 8 bits, then you would have all of those and then one store signal. So what you would do is get a bunch of data latches and then connect each byte to the data signal and then each of the inputs to the store and then output that. That would be like how to store 1 byte of data. And then you use a bit of more fancy stuff like picking which address you want to do, and then you have RAM.
And the tri-state stuff?
Maybe in a few more years.
It gets a little more complicated with buses and.
Yeah, plus I tried to normalize it to 1 topic per talk, or like 1 topic per year, because last year I did that part, telling how to add and subtract signals. And maybe next year I could tell you how to display numbers with the 7-second display. And then maybe after that I could talk about tri-state and the tic-tac-toe circuit.
And then year after that we finally get to SHA-256?
Yes. Okay. I think there were 2 things posted.
Questions?
I can't relate. What's the software that's being used here?
It's called Digital Logic Sim, and you can get it on itch.io.
Yeah, Digital Logic Sim by Sebastian Lake is
If you watch his videos, you realize that I do pretty much exactly what he's doing.
And he's a independent game developer, so Silas poured over all of his videos and considers him one of his teachers. Any other questions? So we're doing a homeschooling panel later this afternoon and talk a little bit about our process for this. And I believe Ellie has a question. You're going?
Oh,
Go ahead.
no, could you show us the tic-tac-toe game?
Sure.
Do you have tic-tac-toe on here?
Yes.
Could you play a game of tic-tac-toe with Dad? You don't
I
have to
still
show how
haven't
you made
introduced
it.
the tri-state, which is a big part of tic-tac-toe.
It's okay. You don't have to. Just show the final result.
Okay. I guess so. Tic-tac-toe. I'll add on this. So it's a lot easier to see the input when they're all connected to one pin, but that pin has nothing to do with the thing. It's only the inputs. So right now all of them are off. I want all of them to be tri-state instead.
Can you just say briefly what tri-state means?
It means black. Like for all. Also, by the way, a NOT gate applied to nothing is it's on, so it's that instead. So tri-state is like I haven't showed you this yet, but you can die the things individually, but you can't have a circuit that does that automatically. So what you do is you use black, which is tri-state. It has a bit more purposes in logic, but I tried to use it as just like the third color where no one's been there yet. Okay. So, Dad, you go first.
Okay, so I will. So tic-tac-toe, as you know, is we'll treat it as a 3x3. And then,
I can't do that, so instead, this is just row by row. And you try to get like here, skip 2, here, skip 2,
to get 3 in a row, you need to have. What did you call the arithmetic?
progression. 3 things. So, Dad, do you want to be in circles or crosses?
I'll be crosses.
Okay.
I'll go top, middle.
So top middle. Wait, top middle is 2. And then, yeah, it works. So I know where to go in that piece. Circle. I'll go right here.
So it stored my move in the first bucket.
Awesome, now it's flickering because it doesn't know what to do. But tri-state doesn't affect the output at all, unfortunately.
So you went.
Part with tri-state's backstory.
Okay, then I'll go. What did you do? Is that middle?
Yeah.
Okay, I'll go top left. 1.
Okay. What happens if you do both of them? I never tried this before. Oh, it just uses one of them. Okay, well, that's why I have an undo button. So I guess I'll go. So I guess I'll reset that. Okay. Wait, what? I wanted it to be crosses. Okay. Now I can see what you're doing. So this is number 3.
Story.
Yeah.
Oh, you foiled my plan.
Well, now, in normal tic-tac-toe, you would see that I am having middle and top right, but right now, you can see I'm trying to do this, skip this. So will you go there, or will you let me?
I'll let you. I'll go 9.
Why?
Okay, I'll go, so that's 7.
Yeah, it's 7. Fold my plans again. Well, now this is very hard to catch, but this, skip to this, skip to this, a lot even. Also, I just realized I got 3 more.
You have 3 in a row?
Yeah.
But it's still not, it's not a winning state, right?
Yes, it is. I just haven't implemented it yet. And even if I did, I would have to brute force it, and I would somehow have to tell it what's the difference between off and tri-state.
Can you show the circuit of implementation?
Sure. I make stuff like this all the time. Because like in part 3, in like the 4th talk, stuff is gonna look pretty much exactly like this. Also you can look like this, and this is just a piece of code.
Okay.
Okay, so 3rd postscript.
It's PPS.
Yeah. PPPS.
Okay, thank you for coming.
Now it's time for an ad.
Oh, time for an ad. Yes, so we developed that puzzle game back there, the 3D puzzle.
You turn around using it.
Ellie's holding it up. Silas gets a $5 commission for every sale. So,
Also, I should probably just say, shout out to you and you and you and you, I think, and you. And you and you. I think that those are the people who are turning me.
thank you. Thank you for coming to NextGen.